Welcome, my dear student. Myself, A. Venkatesan, Assistant Professor, Department of Mathematics, St. Joseph College of Arts and Science, Kadalur. In this video, we're going to learn complex analysis. It is the Unit 1, Part 5 video. In complex analysis, we're going to see exponential form of complex number, roots of complex number, nth root of unity, roots of unity, and some problems based on roots of complex number. So first thing, we're going to see exponential form. We know what is complex number and complex plane. So what is complex number? Z can be written in the form x plus iy, where x and y are real numbers, and we call x is real part and y is imaginary part. Also, we can know how to plot a complex number. So let us see this figure. So we can plot a complex number z equal to x plus I. So from this plane, we convert exponential form. So how to convert? So what is r? R is the distance from origin to the particular point. So now we join this z to the horizontal axis. So we can create a line, this one. And the opposite side is y and adjacent side is x. The given angle is theta. So therefore, we are using trigonometric formula cos theta equal to adjacent side by hypotenuse. So therefore, that cos theta equal to x by r. So from this equation only, we can get the value of x equal to r cos theta. Similarly, sin theta equal to opposite side by hypotenuse. So sin theta equal to y by r. So that is y equal to r sin theta. So therefore, we can write the complex number z equal to r e power I theta. That is r of cos theta plus I sin theta can be written in r e power I theta. So this is the polar form of complex number or exponential form of complex number. And another one important, in this radius, in complex analysis, the real number r is always taken positive, not allowed to be a negative number, because it is the length of the radius vector. So that is we denoted as r vector equal to the mod, that is r equal to mod z. And also the theta represents an angle measured in radians that z makes with the positive real axis, and those values can be determined from the equation tan theta equal to y by x. That is theta equal to tan inverse of y by x. And another one, each value of theta, that each one value is called an argument of z, and collect all theta, that is such values is denoted by, and set of all such values is denoted by RPZ. The principal value of RPZ is denoted by RPZ. The small difference is the first letter should be used in a caps A, and the unique value is theta such that theta is lies between minus pi to plus pi. So therefore, we can write RZ equal to the principal argument Z plus 2n pi I, where n is varies from 0 plus or minus 1 etc. When z is negative real number, that argument has value pi only, not minus pi. So using this idea, now we are going to find roots of complex number. We know what is the roots of real number, and what is how to find the roots of any algebraic equation. So like that, now we are going to find the roots of complex number. So what is the exponential form of complex number? Z equal to r into e power I theta. So if you take this z equal to r into e power I theta, So it looks like a circle centered at the origin with radius r. And theta is increased. Z moves around the circle in counterclockwise direction. In particularly, that when theta is increased by 2i, we arrive at the original point. Again, we meet the same point. Suppose if theta is decreased to 2pi, again it will be the same. Suppose if you take two complex number, looks like z equal to r into e power I theta and z1 equal to r1 into e power I theta, and we want to say both are equal if r1 equal to r2 and another one important, the theta equal to theta 2 plus 2k pi. That is because the radians it will be the difference. So we add the small differences to k pi. In this observation, we may write in a general one as z to the power n equal to r to the power n into e power I n theta. So using this idea, so now we are going to find nth root of any complex number. So now let us take two numbers z0 and zn. By this observation, we equating these two. So we know the last one, how two complex numbers are equal, that r and theta can be find something. So like that, r power n equal to r0 and n theta equal to theta naught plus 2k pi. So we want r, so take nth root of r. So therefore r equal to r0 whole to the power 1 by n. And from the n theta we divide n, and theta equal to theta naught plus 2k pi divided by n. So we get r and theta. So now we substitute this r and theta in z because we need nth root of any complex number. So we know z equal to r into e power I theta. So therefore in place of r, r0 equal to the power 1 by n, theta equal to theta naught plus 2k pi by n. So we expand this one and we getting the modulus. So that is equal to r0 whole to the power 1 by n exponential of I into theta naught by n plus 2k pi by n. So we know the exponential of modulus term is 1. This mod e power I theta equal to 1 because mod means square root of real part square plus imaginary part square. So that is cos square theta plus sin square theta value is 1. So therefore mod z equal to r0 whole to the power 1 by n. That is, this roots lies in the circle about the origin. They are equally spaced at every 2k pi by n radians, starting with the theta naught divided by n. So let us see this figure. So it is equally spaced with the radians. So every radius are equal because it forms a circle form. So r0 nth root of unity, and the radians having 2 pi by n, that is the angle theta 2 pi by n. So in general we may write the nth root of unity as ck equal to r0 whole to the power 1 by n exponential of I into theta naught divided by n plus 2k pi by n. So this is the nth root of unity for any complex number. So now we are going to find the nth root of unity, that is the nth root for 1. So we know the nth root of any complex number ck equal to c0 into omega n to the power k. So now we can consider 1. So 1 can be written e power I0. So that is equal to, we find argument z means we collect such a collection of all thetas. So therefore we can write I into 0 plus 2k pi. So therefore 1 equal to e power 2k pi. So now we apply nth root. So 1 to the power 1 by n equal to exponential of e to the power 2k pi I whole to the power 1 by n. So this implies that 1 to the power 1 by n equal to exponential of I into 2k pi by n. When n equal to 2, the roots lies at vertices of the rectangle polygon inscribed in the unit circle mod z equal to 1. So in general, you may expand this one, nth root of n. Wn we know e power I 2k pi by n. So therefore we may write the nth root of unity is 1. Nth root of unity is Wn to the power k. So if you expand this one, we get the diagram looks like that. So first one omega n to the power 3 roots we can find, and 4 roots and 6. Now we are going to see some problem. So what is the first problem? So to find the cubic root of minus 8. So a is equal to minus 8. So we can rearrange the term. Is equal to 8 into minus I. So minus I is the value e power minus I pi by 2, because cos pi by 2 minus I sin pi by 2, cos pi by 2 0, sin pi by 1, so we can get minus I. So therefore minus I can be replaced 8 into e power minus I pi by 2. So therefore we apply the general form z equal to 8 into e power I into minus pi by 2 plus 2k pi. So now we are going to apply the cubic root. So therefore z cubic root of z equal to 8 e power I into minus pi by 2 plus 2k pi whole to the power 1 by 3. So now we apply the cubic root. The cubic root of 8 is 2. And by De Morgan's law, this can be written as exponential of I into minus pi by 6 plus 2k pi by 3. What is De Morgan's law? Cos theta plus I sin theta whole to the power n equal to cos n theta plus I sin n theta. So like that. So the power can be multiplied inside the argument. So therefore, Ck, the general form of the cubic root is 2 into exponential of I into minus pi by 6 plus 2k pi by 3, where k is run from 0, 1, 2. So now we find the values of C0, C1 and C2. So put k equal to 0 in Ck. So we can get 2 into exponential of minus I pi by 6 plus 0. So 2 into e power minus I pi by 6. So now we expand in the exponential form. Cos pi by 6 minus I sin pi by 6. We know the values of cos pi by 6 and sin pi by 6. So therefore we can get C0 equal to root 3 minus I. Similarly, we find C1. Put k equal to 1 in Ck. We get the exponential of I into minus pi by 6 plus 2 pi by 3. So now we are taking expansion. So cos pi by 2 plus I sin pi by 2. So what is cos pi by 2 value? 0. What is sin pi by 2 value? 1. So therefore C1 equal to 2i. And similarly, to find C2, put k equal to 2 in Ck. So therefore we can get exponential of I into minus pi by 6 plus 4 pi by 3. After simplification, we can get cos 7 pi by 6 plus I sin 7 pi by 6. If you want to expand this term, we can get minus 2 3 by 2 minus I into 1 by 2. So therefore we can get C2 equal to minus 2 3 minus 6. So therefore the cubic root of minus 8i is C0, C1 and C2. So now we plot this point in complex plane. What is C0? Root 3 comma minus 1. So root 3 comma minus 1 lies in the fourth quadrant. 2 0 comma 2. 0 comma 2 lies in the first quadrant. This is the axis, y axis. X is 0, y is 2. And third one is minus root 3 comma minus 1, which lies in the third quadrant. So now we join all this line segment and we draw this. The radius are equal. Already we seen the last section, nth root of unity. It's equally spaced the radius. So therefore, the radius is equal and it gives a circle. So next problem, find two values of Ck where k equal to 0, 1 of root 3 plus I. Let us find the square root of root 3 plus I. So let's take z equal to root 3 plus I. So the last sum, only the imaginary part is given. Here, real and imaginary part is given. So at that time, we can easily change the I. There is no problem. Here, the real part is also there. So now we change this form z equal to r into e power I theta. Looks like we know what is r. R equal to square root of real part square plus imaginary part square and theta equal to tan inverse of y by x. So we using these two formula and we modifying that is z equal to r into e power I theta form. So z equal to root 3 plus I. Therefore x equal to root 3 and y equal to 1. So therefore r equal to root 3 plus 1 equal to root 4, that is equal to value is 2. And theta equal to tan inverse of y by x, tan inverse of 1 by root 3 equal to pi by 6. So therefore we may write that z equal to 2 e power I pi by 6. In general, we may write Ck equal to 2 e power I into pi by 6 plus 2k I pi whole to the power 1 by 2 because we need a square root where k is run from 0, 1. So now we find Ck equal to 0 and k equal to 1. Put k equal to 0, we can get C naught equal to root 2 into exponential of I into pi by 12 plus 0. So exponential of I into that is e power I pi by 2. E power I pi by 2 is cos pi by 2 plus I sin pi by 2. So now we are going to find cos pi by 2 using this formula. We know the cos pi theta equal to 1 plus cos theta divided by 2. But using this formula, we can find cos pi by 2 value. Therefore, the cos pi by 2 value is square root of 2 plus square root of 3 divided by 2. And similarly, we find the sin pi by 2 value using the sin square root of formula. Therefore, we can get C naught equal to square root of 2 into root 2 plus root 3 divided by 2 plus I into square root of 2 minus root 3 divided by 2. Similarly, put k equal to 1 and Ck, we can get C1 equal to square root of 2 into exponential of I into 13 pi divided by 2. Once again, we apply the same formula of cos square theta and sin square theta formula. That is cos 13 pi by 12, we get some answer minus of square root of 2 plus square root 3 divided by 2 and sin 13 pi divided by 12 equal to minus of square root of 2 minus square root of 3 divided by 2. That is, it looks like the opposite sign of C naught. So these are the two roots for root 3 plus I. The next problem, find the square root of 2i. So let z equal to 2i. So if you take z equal to 0 plus 2i, x is 0, y is 2. So therefore r equal to 2, theta equal to pi by 2. So we may write z equal to 2 e power I pi by 2. In general form, 2 e power I into pi by 2 plus 2k pi. Z equal to 2 into e power I pi by 2. So now we take the square root. So z to the power 1 by 2 equal to 2 into e power I pi by 2 plus 2k pi whole to the power 1 by 2. So therefore, square root of 2 into e power I into pi by 4 plus k pi. So therefore, the general term for Ck, we may write square root of 2 into exponential of I into pi by 4 plus k pi, where k equal to 0, 1. Put k equal to 0 in Ck. So we get C naught value. So C naught equal to square root of 2 into exponential of pi into pi by 4 plus 0. So that is square root of 2 into exponential of pi by 4. So square root of 2 into cos pi by 4 plus I sin pi by 4. So we get C naught equal to 1 plus I. Similarly, we can find C1. So we get the value is minus 1 divided by root 2 minus I divided by root 2. So these are the two roots for Z equal to 2I. So similar way we can find any roots of complex. Thank you.